Hey everyone, and welcome back to another Forge College Explainer. I have to admit, my head is still spinning just a little bit. In our last explainer, we were just casually breezing through the sunny skies, integrating services and tooling on Solana Cloud. But today? Well, today we are putting our lab coats back on, grabbing our safety goggles, and diving straight back into the deep end of the Ethereum gas lab. We are tackling analysis techniques and cost-saving comparisons. This is actually a huge part of the gas mechanics and optimization module inside our Ethereum fundamentals course. It's that pivotal moment where your raw data finally becomes the ultimate proof of your engineering genius.
Okay, let's dive into this. Here is our inventor's blueprint for today's session. First up, computing your cost metrics. Second, building optimization scenarios. Third, quantifying your gas savings. Fourth, proving reproducibility. And finally, number 5, the next steps for your capstone.
All right, kicking things off with Section 1, Computing Your Cost Metrics, where we establish the baseline.
So, to get started, we really need our raw materials. That's the beautiful canonical Parquet or CSV dataset you painstakingly cleaned up in Lesson 2. Look, before you can prove you've built a better machine, you need to know exactly how inefficient the current one is, right? And that brings us to our baseline. Your baseline is the original unoptimized state of your transaction. It's kind of like an inventor looking at a clunky, smoke-billowing, steam-powered contraption and carefully noting exactly how much coal it burns before they even attempt to fix it.
Establishing this baseline involves 3 pretty clear procedural steps using Python and Pandas. Number 1, load that clean dataset into a Pandas data frame. And hey, make sure you parameterize the file path at the top of your notebook so you can actually reuse it later. Number 2, compute the base transaction totals. We're talking total gas used and total fee paid, which is just your gas used multiplied by the gas price. And number 3, group your data to produce a per operation breakdown. You just sum up the gas and count the occurrences for each EVM opcode.
Now, when we do that breakdown, we are heavily focused on opgas. This is the specific amount of gas consumed by a single EVM opcode or a higher-level contract action. It's essentially the granular drop-by-drop fuel consumption metric that we absolutely need to track in our baseline summary. Because if your baseline summary doesn't measure at the opgas level, you're honestly not going to know where the leaks are in your smart contract machinery.
Moving right along to Section 2, building optimization scenarios, or, as I like to call it, designing the better machine.
So we have our baseline metrics securely saved. Now comes the actual invention phase. It's time to take those optimization ideas you scoped out in Lesson 1 and construct some alternative scenarios. And this brilliantly illustrates the conceptual leap we're taking here. On one side, we've got our baseline state, maybe a gas-guzzling, unoptimized loop. On the other side, we have our optimized scenario, utilizing a sleek packed storage pattern. We're essentially using our dataset to simulate exactly what that structural change does to our costs.
Simulating these optimizations really just means applying deterministic dataset transformations to a copy of your dataset. How do we actually do this? Well, you might reduce the opgas for a specific opcode by a set percentage to model an opcode level optimization. Or you might merge repeated operations to simulate call batching. You could even just drop redundant operations entirely if your earlier trace analysis found some useless steps. But the absolutely crucial thing here is documentation. You've got to document the exact code used and provide a short rationale for why this transformation makes sense.
Okay, I have to give you a very playful but very serious warning here. Always use the exact same aggregation code for your scenarios that you used for your baseline. I really can't stress this enough. If you calculate your baseline totals using one aggregation function and then get super creative and use a completely different method for your scenarios, you are no longer comparing apples to apples. Your metrics will be completely useless and your data is going to lie to you. Just keep the math consistent.
All right, Section 3, Quantifying your gas savings. Let's get to the patented proof.
This is honestly the most exciting part of the blueprint. We're crunching the numbers to reveal the exact hard math savings our optimizations actually generate. This side-by-side comparison you're looking at, this is the absolute MVP of your capstone report. Notice how it lines up the baseline metric right against scenario A, explicitly calculating both the absolute delta and the percentage delta. Dropping from 123,456 gas down to 100,000 yields a clear absolute savings of 23,456 gas.
Now, what's really interesting about this slide is that 19% figure. That percentage drop is the ultimate reward for all your rigorous data analysis and Pandas scripting.
It is not just some math artifact, it's definitive proof of an almost 1/5 reduction in operational cost. When you present this, you aren't just a developer anymore. You are a verifiable cost-saving engineer.
But remember, raw numbers, even incredibly impressive percentages like that, aren't quite enough to seal the deal in a professional report. You've got to include a short interpretation paragraph translating those deltas into real-world impact. Like, what does a 19% reduction actually mean for us? Explain how many transactions would need to adopt this optimization to reduce a protocol's monthly gas spend by a tangible dollar amount. You really have to make the numbers speak to the real world.
Almost to the finish line. Section 4. Proving reproducibility. It's time to check the math.
So, we have our amazing savings, but now we have to ship to the final engineering step, ensuring your brilliant blueprint actually works when someone else tries to build it. We accomplish this through a reproducibility check. This is just a final script or notebook cell that reruns all your key aggregations from scratch and mathematically asserts that the fresh results perfectly match your saved values. It is your ultimate defense against weird floating point math betrayals or unseated random number generators.
To confidently tag your notebook as milestone complete, you have to pass a rapid-fire list of essential checkpoint tests. Check 1. Your data load schema has the right columns. Check 2. Your baseline totals match your Lesson 2 records perfectly. Check 3. Your optimization scenario logic is fully deterministic. Check 4. Your in-notebook computed values align with your saved CSV table consistency. And the ultimate test, check 5. You literally must be able to restart your Jupyter kernel, run all cells from top to bottom, and get the exact same outputs.
And finally, Section 5, next steps for your capstone. Let's wrap up this blueprint.
So, the crucial point is, by systematically working through this lesson, you now possess the raw CSVs, comparison tables, and interpretation notes required to build a rock-solid capstone foundation. Visually summarizing that journey looks something like this immensely satisfying chart. You can clearly see a statistically significant, undeniable stair-step drop in gas costs from your baseline, down to Scenario A, and ideally even lower for Scenario B. It's just beautiful visual proof that your optimized machine performs exactly as modeled.
Which leaves us with one final, provocative question for you to ponder. How will you translate these perfectly quantified savings into prioritized, cost-benefit recommendations? Look, having the numbers is absolutely fantastic, but translating those scenario deltas into real business arguments is your next great challenge. And that perfectly sets the stage for our next lesson. You've done truly incredible work today. Congratulations on successfully completing this intense lab work and hitting this massive milestone. Remember, this explainer was brought to you by Forge College. For more in-depth Web3 resources or to explore the rest of the Ethereum fundamentals track and master everything from smart contract architecture to gas optimization, be sure to visit forge.college. Keep building, keep optimizing, and we'll see you in the next one.